Introduction: the Fortran program from 1970, developed 55 years ago, originally created at IIT Kanpur by Pradeep K. Suri, was designed to solve a system of linear equations using Gaussian elimination. It reads an augmented matrix, normalizes rows by pivot elements, and performs row operations to convert the system into an upper triangular form. The final step involves back substitution to compute the values of unknown variables. The input consists of coefficients and constants from a set of simultaneous equations, which are processed systematically to determine the solution. This method was fundamental in numerical computing at the time, particularly for engineering and scientific applications. The 2025 Python version of this program retains the same Gaussian elimination logic but utilizes modern libraries like NumPy for efficient matrix manipulation and Plotly for visualization. The enhanced program not only calculates the solution but also presents results using interactive bar and line charts on a dark-themed interface. This improves readability and usability, making it easier for researchers and engineers to analyze solutions dynamically. Python's built-in functions streamline operations, reducing the need for manual looping and simplifying code maintenance. From an AI perspective, this modernized program can be extended for use in machine learning and optimization tasks. Many AI models rely on solving linear equations for regression, neural networks, and data fitting. By leveraging Python's computational efficiency, it can serve as a foundation for AI-driven decision-making systems, engineering simulations, and financial modeling. The transition from 1970 Fortran to 2025 Python highlights the evolution of computing power and how fundamental numerical methods remain essential in AI and data science today. Result: x equals -2.00, y equals 3.50, z equals -4.50. W equals 17.50. How this below program in Fortran will help in AI. This image contains a Fortran program written by Pradeep K. Suri in 1970 at IIT Kanpur for solving a system of linear equations using Gaussian elimination. Gaussian elimination, also known as row reduction, is a method in linear algebra used to solve systems of linear equations by transforming the system's augmented matrix into a row echelon or reduced row echelon form through elementary row operations. The equations are handwritten on the right side, and the matrix representation of the system is shown below. The program reads a set of equations, performs row operations to convert them into an upper triangular form, and then solves them using back substitution. This program demonstrates Gaussian elimination, a fundamental technique in linear algebra, which is widely used in artificial intelligence, AI, and machine learning, ML. Here's how it can help with AI. 1. Solving systems of linear equations. AI and ML often involve solving simultaneous linear equations, especially in optimization problems, regression models, and neural networks. Gaussian elimination helps find unknown variables, weights, biases, etc., in equations that represent AI models. Example in AI. In linear regression, we solve equations to find the best fit line by determining optimal coefficients. In neural networks, weight updates rely on solving linear equations in backpropagation. 2. Data pre-processing and feature engineering. Many AI applications, like image processing, speech recognition, and NLP, natural language processing, require solving linear equations to transform and normalize data. Gaussian elimination is used in dimensionality reduction techniques such as principal component analysis, PCA, which improves AI model performance by reducing redundant data. Example in AI. Facial recognition systems use PCA to reduce image dimensions before feeding data into deep learning models. 3. AI in robotics and control systems. Robots and autonomous systems use linear equations to calculate motion paths and balance forces. Gaussian elimination is used to solve kinematics equations for robotic arm movements. Example in AI. Self-driving cars use matrix-based algorithms for real-time decision-making in navigation. 4. Deep learning and optimization. Training deep learning models often requires solving large-scale systems of equations. Gaussian elimination can be used to invert matrices, which is critical in deep learning optimizers such as Newton's method. Example in AI. In image classification, Convolutional layers process pixel data as a system of equations. 5. Reinforcement learning, AI for decision making. Many AI applications in gaming, finance, and robotics use Markov decision processes, MDP. Gaussian elimination helps solve Bellman equations, which are used in reinforcement learning. Example in AI. AI playing chess or Go solves linear equations to evaluate move probabilities. How visualization helps AI engineers. Bar chart plus line chart combination helps visualize how different variables, x, y, z, w, contribute to a solution. Useful for analyzing relationships between different parameters in AI models. Interactive graphs with Plotly, 2025 Addison. AI engineers can adjust equations and instantly see how solutions change, aiding in hyperparameter tuning. Dark theme for better clarity. Help AI researchers work comfortably in low-light environments. Conclusion, AI-driven impact. This program provides a foundation for solving complex equations used in AI-driven decision-making, optimization, and predictive modeling. Gaussian elimination is a core mathematical technique for AI applications such as machine learning, robotics, deep learning, and reinforcement learning. Bar and line charts enhance interpretability, making AI solutions more transparent. This is a powerful tool for AI researchers, ML engineers, and data scientists. Thank you.